Welcome back, Pre-Calc. Our objective for today is going to be to apply the fundamental theorem of algebra. I've got the checklist on the screen. You know what to do from here. So the fundamental theorem of algebra says, and you do not need to write this down because we're going to really practice this theorem in application soon, but it says a polynomial function of degree n has exactly n complex zeros, and complex can be real or non-real, okay? And some of these zeros may be repeated, so not all your zeros have to be unique. So a consequence of the fundamental theorem of algebra is that every polynomial can be factored into n linear factors, where again, n is the degree of the polynomial. So if you have a cubic polynomial, so degree 3, you are going to have exactly three linear factors. Those factors do not have to be unique from one another. So again, you can have repeats, and some of your zeros could be imaginary, right? Because it's all complex, so real and non-real. All right, first pause on your screen. Can you go ahead and copy this sentence, and then we'll fill it in together. So this says if a complex number a plus bi, where b is not 0, is a zero of a polynomial function with real coefficients, then its complex conjugate, do you remember what that is? That's going to be a minus bi, is also a real zero, is also a zero because our polynomial has real coefficients, okay? Why do we need both? Well, again, if I want to end with real coefficients, I can't have any of these i's once I multiply everything out. And so I need kind of the opposites. I need the complex conjugate in order to get that nice cancellation that we need. Let's see if I can convince you here. So if I have a plus bi times its conjugate a minus bi, this is a difference of perfect squares, right, in factored form. So this is the same as a squared minus bi squared, right, if this is in the factored form. So a squared is just a squared. But what is I squared? Do you remember? I squared is -1, so I have b squared times -1. I still have this negative, so this becomes plus b squared. And the point is, now my i's are gone, right, because of that complex conjugate. So the point is that your complex numbers that are in this format, where you have an I, they always come in pairs. And again, the reason is so that we can get rid of that I. So let's try example 1. We just write example 1, part A. It says, given that the following numbers are zeros of some function with real coefficients, what other numbers do we know are zeros? Okay, so if I have -2 plus 5i, what else has to be a 0? -2 minus 5i. All right, go ahead and write B in your notes. I've got 2 zeros this time. I have 4i and -7i. I'm going to force a pause on your screen. You tell me what other 2 zeros have to be zeros of the given polynomial. So we should have gotten -4i and 7i. Notice that neither of these had this a part in them, so you're just going to flip the signs, and that'll get you that nice cancellation. All right, and force a pause on your screen. Can you please write example 2 as well as f of x in your notes? All right, so we want to find all the zeros, and exactly how many zeros should we have? We should have 4 because this has degree 4. Again, those zeros may repeat. They may not necessarily be real, but I should have 4 zeros, okay? So what we want to do is start with, always ask yourself, hey, can I factor this? And what I see is, well, these are actually both perfect squares, right, with subtraction in between. So let's start by factoring our difference of perfect squares. So square root of 81x to the 4th is going to be 9x squared, right? And then I'm going to have 1 plus, 1 minus. And then do we know the square root of 625? That's a big one, but it's 25. Okay, and so if I were to distribute this all back, I'd end up back where I started, right? But we want to keep going. We're trying to get this into linear factors, right? So I'm going to take this second factor that I have here, this 9x squared minus 25, and that's another difference of perfect squares, right? So this would be 3x plus 5 and 3x minus 5, and that's good news. There's 2 linear factors, okay? Now I need to do the same thing here. Now this is almost the same as the second factor. The only difference is what? It's this plus, right? And so that's not going to let us use the difference of perfect squares over the reals, but if I include my imaginary numbers, if I do all complex values, then we can go ahead and factor this, okay? So what we're going to do is we'll have 3x plus 5i and 3x minus 5i, okay? Why don't we multiply this back out to make sure that we're convinced that we get that. So this is going to be 3x times 3x, so there's your 9x squared, right? Now look at what happens to your middle terms. They're exact opposites of each other, so those will cancel, right? Now, if I take this plus 5i to this negative 5i, I'm going to get negative 25i squared. But what is I squared? I squared is negative 1, so I do indeed get back here, which is where I want it to be. If you still don't like that, you're like, Mrs. B, I wouldn't have seen that. Take that, 9x squared plus 25, and set it equal to 0. Because remember, we can grab our factors from our zeros, right? So if I were to set this equal to 0, I'd start with that, right? And then I'm going to divide by 9, right? And then I would take the square root. Now, when you square root, when you introduce a square root, you need to introduce a plus or minus, right, into the equation. So square root of 25 is 5, square root of 9 is 3, but it would be I because I'm taking the square root of a negative number. So I've got here my two zeros that correspond with these two factors, right? So however you want to do it, but now we have all four linear factors. All right, to enforce pause on your screen, can you write example 3 and the f of x, please? Okay, so it says the given function has 3i as a 0. As soon as I see that, I'm like, ooh, that has an imaginary piece. Let me make a note to myself that what else is a 0? Negative 3i. How many more complex and how many more real zeros are there, and how can we find them? So how many more complex? Well, complex is total number of zeros. So in total, how many zeros do we have? We have 3. We were given one of them, so in total we have 2 more. How many more real zeros? Well, I know I have 3i, meaning I know I have negative 3i, so those have to come together. Those have to come in pairs, right? So I must have 1 0 that's real, has no imaginary piece to it. All right, so now let's go ahead and find these find all the zeros. So some people look at this polynomial and they're like, ooh, I can factor that by grouping. Yes, if you know how to do that out of my math lab, great. There might be some that you can't factor by grouping, so go ahead and follow the steps with me here. So what I'm going to do is work with what I know, and I know that 3i is a 0, which allows me to divide by a factor of x minus 3i, and I could do synthetic division here. So set this up with me. Since 3i is a 0, and put it in the corner, grab my coefficients, right? And now let's do synthetic division. We're just going to have to be really careful because we are, we have some imaginary pieces here, and we just got to be mindful. So we're going to bring down this 1, then we're going to multiply, so 3i. Now we're going to add, so it's going to be 1 plus 3i, right? So now we need to multiply this 3i to this binomial 1 plus 3i, okay? So 3i times 1 is 3i. 3i times 3i, let's think about that. 3 times 3 is 9. I times I is I squared, and what is I squared? Negative 1. So I've got 9 times negative 1, so I'll be negative 9, right? Now I want to add these. Well, that is convenient for us because the 9's cancel, and I just get 3i. Now I'm going to multiply 3i to 3i, and we already said that that was negative 9, right? Good news. We should end with a remainder of what? A remainder of 0. Good. Okay, let's keep going. Since 3i is a 0, we said, hey, negative 3i is a 0 as well. So let's go again with negative 3i in the corner here, okay? So I'm going to just be very careful. We're going to bring down the 1. Now we're going to multiply negative 3i times 1 is negative 3i. Add straight down, that's 1. The 3i's cancel. And 1 times anything is itself. How great, we got a remainder of 0 again, which is what we want, okay? So I took a cubic and I divided twice by linears, so this should be my last linear factor of 1x plus 1. So if I want to factor f of x into all its linear factors, I would have x minus 3i, x plus 3i, and 1x plus 1, or x plus 1. So that final 0 was negative 1. All right, can you write example 4 in your notes and then also just these two values? Okay, so the directions for example 4 say write a polynomial with least degree given the following zeros. So I've got negative 1 and I've got the 0 of 2 plus 5i, right? Which means I have what other 0? 2 minus 5i, okay? So here are my 3 zeros. Let's set this up, again, least degree. So f of x is going to be x plus 1, right? Always x minus your 0, so x minus negative 1, so x plus 1. Then x minus this 0, so x minus quantity, 2 plus 5i, right? Be careful with your parentheses there. And then x minus quantity 2 minus 5i. All right, so that's our setup. So now we basically just want to multiply all this through. So here's what I'm going to encourage you to do. Let's leave this x plus 1 to the end and we can just distribute that binomial. And let's work on these second two factors, okay? So first, let's go ahead and distribute this negative here and this negative. So I'll have x minus 2 minus 5i and x minus 2 plus 5i, okay? Now, we could distribute the x to all three terms, the negative 2 to all three terms, the negative 5i to all three terms, combine, and then come back into the x plus 1. You can do that if you really want to. But let's see if we can't use some algebra savvy to make our lives a little bit easier. Here's what I want to remind you of. If I have a minus b times a plus b, that's the difference of perfect squares in factored form, right? This is equivalent to a squared minus b squared, okay? Here's what I want you to think of it this way. Think of x minus 2 as your a, and think of 5i as your b. See how you have a minus b times a plus b. Do you see that? So again, in our case, a is x minus 2, and b is 5i. So all this orange stuff I can simplify to a squared minus b squared. So let's do that. Well, a, again, we said that was x minus 2. There's my a squared, minus b is 5i. So 5i squared, right? And I'm just going to keep writing this x plus 1 to the left here. I'll deal with him at the very end. Okay, let's keep working with the orange piece. So now we can do this just distribution in our heads a lot easier. If I distribute x minus 2 quantity squared, remember that's x squared minus 4x plus 4. And then 5i squared is what? 5i squared is negative 25 times a negative 1. That's going to be positive 25. And then 4 plus 25 is 29, right? So why don't we just make this a 29. You okay with that? Save us some steps here. Okay, so instead of distributing 3 terms to another 3 terms, we were able to do this in 2 steps. All right, so that saves us quite a bit of time. All right, now just distribute this x to all 3 terms and the 1 to all 3 terms, combine like terms, and then hit continue when you're ready to check your answer. I've got my final answer there on the bottom in blue. And just FYI, it's never a bad idea to go ahead and graph the polynomial and see, oh yeah, okay, only crosses at x equals negative 1. So negative 1 is my only real 0, which matches up with what I have here, right? The other 2 zeros were non-real. So go ahead and summarize in one sentence for me, and I'll see you all next time.